Bayes' theorem is a way to take probabilities based on existing known data and update them based upon newly acquired information. To use Bayes' theorem, you have to first know the total probability rule, and it is right here. That in our case, the probability of A is equal to the probability of A and B happening plus the probability of A and happening and B not happening. So we're looking for A right here. It's going to be the entire circle that we have for this outcome. Well, what's the two parts of the circle? The probability that A happens while B happens, this red side over here, and the probability that A happens when B doesn't happen. It gives us the total probability of A happening compared to this mutually exclusive alternate event. And we can use that information, in this case, to use Bayes' theorem. This formula looks really, really scary on the bottom. It's not as bad as it looks when you put it in a chart form, which I'll get to in a second. But what we're going to do is we're going to take the prior probability, the probability that we knew already, and we're going to update it based upon new information that we have to make what they call the posterior probability, the conditional probability, how this is going to change if a certain event happens. And our posterior probability, in this case, we're going to call P is B given A, can be found using this information down here. Firstly, this is the formula for B given A. It's always the probability of both events happening divided by the probability of the event happening that was given. All we're doing in these other formulas is just expanding upon it. So down here on the bottom, that probability of A is just this formula. We just substituted in this formula right here that the probability of A is always equal to the probability of A and B plus the probability of A and the complement of B. And then in the third step over, we're going to go through and we're just going to change the setup of these formulas to expand them a little bit more. So the probability of A and B is going to be given, it can be re-expressed, as the probability of A given B divided by the probability of B. The probability of A and B, same thing over here, it's the same setup, plus the probability of A and not B, which can be rewritten as the probability of A given that B didn't happen times the probability that B doesn't happen, the joint probability, if you will. So it's the same formula, we're just making it much, much bigger so that we can change the individual parts within the formula. Let's put it in a practical example right here. We have a lie detector test, and an individual is asked to answer a series of questions while connected to the polygraph, the lie detector. These things aren't all the time accurate, and some people will go in and they'll still lie even though they're on a lie detector test. And we have the following information to work with. 99% of the people that go in for the polygraph test are going to tell the truth, while the other 1% are liars because of the complement rule. These tests are 95% reliable, which means that when somebody lies, there's a 95% chance that it gets picked up, but 5% of the time somebody gets away with lying. These are the way that polygraphs work is they're based upon physiological changes to your body. So like when people lie, they tend to get more nervous and the test can check it out. But some people will just be so nervous and the test false reads and it thinks that they're lying because of the way that their body's reacting to being in that situation. And we are estimating here that there's a 0.5% chance that event's going to happen. If someone's going to come in, they will be honest to goodness, telling the truth, but because of the way that they're acting during the lie detecting test, about 0.5% of the time, it's going to come up thinking that they're lying. So if an individual has taken the polygraph test and the test detected a lie, what's the probability in this case that they were actually telling the truth when the test said that they were taking a lie? Well, let's go through and figure this out. Let's set up our probabilities. Probability they tell the truth, 99%. Probability they don't tell the truth, the complement of telling the truth, is 1%. The probability that it detects a lie when someone's not telling the truth is 95%. The probability that it detects a lie when someone's telling the truth is only 0.5%. And we can plug all those numbers into Bayes' theorem. And that's what we have down here. So we just find the joint probability of the probability that it detected the truth, or detected a lie given that someone was telling the truth, times the probability of them telling the truth. That's the top. And at the bottom, we have the probability to detect a lie when someone was telling the truth, times the probability of them telling the truth, same number, times the probability to detect a lie when they were not telling the truth, 95% accurate, times the probability that someone's going to lie, which is 1%. And it comes out to 0.3426, about 34% chance in this case that if we're going through that this thing is going to detect a lie when somebody is telling the truth, like when it goes off. But we can break this down into a table, which just makes it easier, in my opinion, than having to throw it in the formula. I mean, yes, you can throw it in the formula once you have it memorized. This is just easier to break down right here. So how did we come to these numbers? The prior probability that we had right now was that there's a 99% chance of them telling the truth and a 1% chance of lying. Our conditional probability that we had here is that the numbers we used up above detects a lie when someone's telling the truth only a half of 1% of the time, while it detects a lie when someone's lying 95% of the time. Our joint probability is just the two multiplied together, so our probability of detecting the truth and someone is telling the truth, detects a lie when someone's telling the truth, it comes out to 0.00495. Same thing down here gives us 0.00950. And the probability, in this case, that it would detect it is 0.01445. So what about our posterior probability? How does it change? Well, this number right here, 0.34256, is just the top up here, 0.00495, divided by the probability down here. So probability that it detected a lie and someone was telling the truth divided by the probability that it's going to detect a lie gives us our answer. And if we're looking for the other way around, the complement of this, well, it's just 1 minus what we got is our answer.